So hi everyone, my name is Yaniv, I'm from the Container Services team. And in the last few months, I've been actually leading our AI and ML solutions on solutions like Kubernetes, for example, and I'm going to show you why in a couple of minutes. And I also have Mike Root with me, who's a senior engineer on the open source team here in AWS as well. And he's actually going to show you a pretty nice demo on some of the things that we've been doing and the innovations we've putting into solving some of the specific challenges that people have today on running their machine learning workloads. So let me start off by just saying that there's been a lot of hype around machine learning and AI over the last few years, and Gartner keeps running an annual report and survey on the hype cycle of these kinds of emerging technologies. And each year, machine learning and AI are kind of in the peak of their hype cycle. So it's coming to a tipping point in which the hype around this technology is actually starting to transform to real impact on businesses like enterprises, large companies, and also startups who are all looking to leverage and gain the benefits from what it is. And there has been a recent IDC report that shows that, or predicts that in the next year or so, about 40% of the digital transformations are going to be involved with AI and ML. So this is just to kind of set the stage on why we're even seeing this and how meaningful that can be for you. Our mission at AWS is to be able to put machine learning in the hands of each and every one of you. To do that, we have built the broadest and deepest compute platform to help support AI and machine learning workloads on multiple stages. So for the expert machine learning practitioners who want to have the control and the ability to deploy and develop, test, deploy, and tune their own machine learning models, we have built frameworks that can run on our compute services. As you probably know, we have a pretty broad range of compute offerings from P2s and P3s, the G instances, the latest announced P3DN, and some others that are right now in the works, such as G4 and the new chip Inferentia, which we announced that is going to be launched later on. So, and on those compute platforms, you can actually run a selected number of frameworks and interfaces of machine learning, including TensorFlow, MXNet, and many, many other flavors as well. On the middle layer, we have what we call the ML services, because unfortunately, as it is today, there are not enough machine learning experts and specialists in the world. So in order to put machine learning in the hands of each and every one of the data scientists, data engineers, and machine learning practitioners, we invented a bunch of machine learning services fronted by SageMaker, who is an end-to-end compute platform and machine learning platform destined to be able for you to get started with machine learning very easily, starting from the notebook experience, so you can provision Jupyter notebooks, following on with data preprocessing, training, and then inference as well. So it's a package that allows everyone to get started with machine learning very easily, and also comes pre-built with a lot of the models and the public, more popular models that are serving a lot of our customers to get started with machine learning. And then on top of that, we also produced a bunch of AI-specific platforms that are for those of you who do not want to be able to model and build and train their models, but just wanted to be able to leverage AI as part of your applications with a bunch of AI offerings such as vision, speech, language, and many, many others. We introduced a bunch of managed services like recognition, comprehend, and many, many others, which you can just leverage with your existing or new applications running in the cloud and get started very easily. And also drive the time to market and the cost significantly down. So to summarize all of that, a very deep, in terms of breadth and depth, compute and AI platform that allows each of you, whether it's an expert machine learning practitioner, somebody who's getting started, or just want to leverage our capabilities, to do that with our services. Now, obviously, you cannot do machine learning with just AI and ML services. Machine learning usually requires a lot of data processing, and so you need analytics tools such as EMR, Redshift, and other services to be able to help you digest, pre-process the data, and make it available for your machine learning development lifecycle and training. You also need a lot of storage. As I will show you a little bit later on, some of the customers that we work with, especially in autonomous vehicles industry, are processing huge amounts of data. And to do that, they are leveraging a lot of our S3 services, including Deep Archive, which is very popular in that space, in order to gain the benefits of saving a lot of data and making it accessible to your application and training and inference models in the fastest way and in the cheapest way possible. But the reason we're all here is Kubernetes. So Kubernetes has been becoming very, very popular in a framework layer in order to run these machine learning processes or pipelines end-to-end on the platform. And this is what I'm going to focus on today to show you what customers are using it for and how you can leverage that with AWS. So first off, why would we use Kubernetes to run machine learning? I mean, Kubernetes is a general purpose compute platform, container platform, orchestration. Why would you use it? So people are using it from exactly the same reasons why they are using Kubernetes for their microservices, for their apps, or any other application for that matter. So the ability to compose a lot of different pieces and building blocks and build your own customized machine learning tool or framework using your favorite models, using your favorite IDE tools, and choosing each step of the way which component or which technology you want to leverage, that's something that Kubernetes and the frameworks that run on top of it will provide to you. Portability, so the ability to actually take your machine learning workflow from your laptop or your desktop GPUs to anywhere else, including the cloud, and be able to remain consistent along the process and have the exact same pipeline running on all environments. And obviously scalability, which is something that Kubernetes offers you, and especially if you're running on AWS, you will get all the benefits of the underlying autoscaling services that we have that really allow you to burst into the hundreds or even more instances, GPUs, or CPU cores as required. So I want to break it down to talk a little bit about the machine learning workflow itself. Let's get down to the details. What do you have to do in order to run your machine learning workloads today? So first of all, people start off with running some prototyping. And usually the way that that works is through either Jupyter notebooks or other types of notebooks. Notebooks, for those of you who doesn't know, are popular technologies in the machine learning space and also analytics in general because they allow you to bring in a lot of code, data, all in the same place and be able to share that with your peers or with other teams in your company and also interact from within that notebook with other services. For example, in AWS, you can actually invoke jobs that are run in EMR or run in Redshift straight from within a Jupyter or any other notebook that you will, because basically it's all API-based. Some other machine learning practitioners prefer the IDE approach, so they like to program and code, so they use Python or frameworks like PyTorch. And then there are others who use frameworks like RBrain, for example, which is a machine learning framework built on top of Jupyter. So it's kind of more tuned into the machine learning workflow. One thing to note about that process, though, is that the process is iterative. So you start off, you prototype, you bring in a bunch of data in order to test and build and train your model. But then after you validate that with real data, you may find that the model is still not where it needs to be, which means it's not really behaving the way it should on data sets that have not been used before, which means you have to go back and do some data wrangling, recompute and tune your model, and then do the same process all over again. So that can be an iterative process that can take however time it is, depending on the complexity of the model. So let's see how that works. So first of all, in terms of Jupyter, Jupyter itself is a very popular technology. A lot of the frameworks, including our own SageMaker, QFlow, which we'll talk about in a second, and others, support Jupyter today. As I said, it's very well tuned to do analytics in general, but machine learning specifically. So, that's very nice. Yeah, let's bring it on. So, as I mentioned, the data processing tool starts, or the machine learning workflow starts with data pre-processing. So data pre-processing is basically bringing in some clean data or raw data that comes in from multiple sources of your application or from your business. That data, first and foremost, needs to be cleansed. Sometimes you need to drop the irrelevant data. Sometimes you're getting unstructured data that needs to be structured into a certain format in order to run the machine learning process on it and build models. So there could be multiple variations of how you can clean and pre-process the data. And then you get into an iterative process in which you're going to build your model, you're going to train it, and then when you do validation, you may have to go back and do some data wrangling, which will be an iterative process like I mentioned before. At the end of the day, you will get a model. And that model needs to be deployed on an endpoint so that it can actually start serving our inference requests, which are what we actually came here to do. We want our application to make a prediction and get a response from, or make an API call and get a prediction from the inference endpoint. So you can do all of the things that I just mentioned today on Kubernetes alone without QFlow. However, when you do so, you will have to take care of a lot of the things yourself. So things like how do I port the UX and the IDE that I want to work with in my desktop, and how do I switch that over to the cloud? How do I use different models? How do I use different tooling? Because the tooling may change or evolve over time. So QFlow really what it does is provides a set of tools that can work across all those environments for you and allow you to just set the stage on how your process should look like and have it run in a consistent manner across all of the places that you're developing your machine learning models with. So what is QFlow? QFlow is a collection of tools that help you as an ML practitioner to get the job done. So we mentioned some of those tools like the Jupyter Notebook, but there are other tools. For example, there are framework operators. So for example, we have TensorFlow operator and MXNet operator. So those are different frameworks for machine learning training that you can leverage each of them using the Kubernetes operator that makes them available to QFlow. And there are other tools in that, like Argo, which is a workflow management system. And I will talk about QFlow Pipeline, which is another component, which is relatively new on QFlow in a second. So the good news that if you want to get started with QFlow on AWS, you can do so today. We have a product page on the QFlow project itself, which has a deployment section that can get you started very easily. So you're going to be installing a bunch of tools like kubectl, ksonnet, obviously the command line for QFlow itself, and then the provisioning process is going to set up the entire EKS cluster, including the QFlow for you. So it's going to abstract a lot of those complexities that data practitioners or machine learning practitioners may run into if they're not aware of the AWS constructs like VPC, EBS, networking, etc. QFlow Pipelines is one of the recently added features to QFlow. What it does is it allows you to actually define a pipeline or a machine learning pipeline end to end. So think about the process that I just mentioned earlier, starting from the data pre-processing, training, and inference. All of those steps can now be represented as a step in the QFlow pipeline. Now, the QFlow pipeline is persistent, so it can be replicated and maintained across environments. And it has a bunch of integrations to other tools that you can leverage to do different steps. So for example, for data pre-processing, you can today invoke an EMR job using Spark. And Spark is one of the most popular frameworks to date on processing large sets of data. So the benefit of using or leveraging EMR is that you will be able to offload the job, get a cluster or a Spark cluster set up for you, leverage spot instances, which is a way for you to reduce the costs with 70 to 90% from an on-demand pricing on AWS, which can be very significant because Spark jobs typically run on large data sets. So we're talking about clusters of dozens or even hundreds of compute-intensive instances that can be costly to process. And this all gives you the ability to invoke all of that from within the QFlow pipeline itself. So some of the benefits involved in leveraging QFlow on AWS, some of which we already discussed. So cluster provisioning with EKS Cuddle, that's basically what it means is it's going to abstract the complexity of setting up AWS constructs and the EKS cluster from you. So with just a simple command line, you can have an EKS cluster with the instance types that you choose and the cluster and the size that you choose set up with QFlow, ready for you to get started with your ML process. We also support ALB ingress controller, which means if you wanted to set up a TensorFlow serving endpoint, you can set it up through ALB ingress controller. So the way it's going to work is we're going to connect an optional plugin, which is the Istio gateway, and all of the traffic coming in from the ALB ingress controller will be flowing through the Istio gateway and then to the ambassador inside the cluster itself. We also have a dedicated support today for storage, and that's not just a QFlow feature, it's a Kubernetes feature. So we have drivers, CSI drivers native to Kubernetes for EBS, EFS, and FSX Lustre. That can be really significant, especially when it comes to large-scale processing, and I'll talk about an example of one of those workloads in a second. Then you also get the unified CloudWatch logging, so all the Kubernetes cluster control plane logs will be routed to CloudWatch, so you can monitor and see what's happening within your cluster. If you're using the ALB ingress, you also get TLS and auth with Certificate Manager and Cognito. And then we recently introduced private access to your Kubernetes cluster, to your Kubernetes API server endpoints, so you can leverage those as well if you didn't want them to be public. And one last benefit is today when you're setting up your QFlow on AWS with the EKS integration, the QFlow will detect if you're running a GPU-based cluster and consequently will provision or install the NVIDIA device plugin on its own. So you don't have to worry about the device plugin manually being installed by you. So this covers all the way to the ML framework itself, i.e. what is the set of tooling that you will use when running that machine learning process. Let's talk about training. So first of all, let's talk about the framework. TensorFlow is a very popular framework that a lot of the developers, and especially on Kubernetes side, love to use. So it's an open source library to develop and train ML models that was created by the Google Brain team originally and can pretty much run anywhere. I think what a lot of people don't know, though, is that today, 85% of all the TensorFlow workloads that are running in the cloud are actually running on AWS. Now, not only that, we actually took the TensorFlow implementation and customized it because what we have found, and we'll get there in a second, but I'm giving you a heads up, a lot of those large-scale training jobs, especially in autonomous vehicles, require what we call distributed multi-GPU, multi-node training jobs. Now, multi-node training jobs means that you need to leverage a lot of GPUs in order to increase your efficiency. But as it happens, the stock TensorFlow, the one that comes pre-built, does not scale as efficient as the number of GPUs. So if you scale your nodes to 256 GPUs, for example, you're only going to get 65% efficiency increase rather than 100. With our tuned TensorFlow algorithms, however, we managed to get it to an AWS optimized fraction of 100% efficiency scaling, which means that effectively, the more GPUs you will add, that's how much your efficiency will increase. Now that's very significant, especially when it comes to GPU instances which are not cheap. And that allows you to basically bring down the overall cost of your training significantly. Now let's talk about one example for that, and that is the autonomous vehicle space. So ever since we launched EKS in June 2018, we have seen a lot of customers running a lot of machine learning workloads, high-scale workloads running, and some of them were from the autonomous vehicle space. So as we engaged, we started to understand what are the requirements that are driving this industry. So it turns out that the autonomous vehicle industry today is at a phase where they're trying to get, and I'm sure all of you know that, to the highest level of automation possible. And as standards go, Those levels range between 0, which means not automated at all, and 5, which is pretty much the nirvana that we are all looking to get, which is we are fully automated, and in terms of control, monitoring, and fallback, this is all being managed by the autonomous driving system rather than the driver or the human. So typically, those customers would range between level 3, 4, if they're really advanced today, and they're all experimenting and deploying in production at the same time. So if a certain company were able to reach SAE level 3, for example, that means they will already have level 4 in their development lifecycle. Now, as it happens, with every new stage of autonomy, the amount of compute required is exponentially increasing, which means that those customers incrementally require more and more compute from both GPU and CPU perspective. Now let's talk about some of the challenges that these customers are facing today. So, as I mentioned, when it comes to training, this is distributed, multi-GPU, and often cases multi-node training. What are the barriers or the challenges that they have told us that they have when trying to run those workloads? So first off, we spoke about this. Machine learning practitioners, they don't want to know VPC. They don't want to know EBS. All they want is to set up their training jobs on their favorite tool, run TensorFlow models or such, and be done with it. Secondly, large data sets on S3, they need to be copied somewhere. And that somewhere needs to be some staging area in the cluster that the job can then read in a very low latency, high efficiency manner in order to run that multi-node training. Next, we have the fact that the data needs to be shared across multiple nodes because, again, this is a distributed job, so all the nodes need to have access to the data. There's also the thing about how do you distribute a TensorFlow algorithm? That's not a trivial thing to do. Now, TensorFlow does have a built-in inherent API to parallelize and distribute the load, but it's not as easy as you would think. So people start coming off and figuring out, hey, is there a framework that can help us do some distributed workloads on TensorFlow in a more easier fashion? And we'll talk about that in a second. And lastly, capacity provisioning is not an easy thing when it comes to those kind of things. Think about this. You need, I don't know, 20 P3, 16 Excels, and not only you need that much, you need them running in a single placement group because you need low latency and high performance network, because typically what happens in a distributed job, there's a lot of parameter exchanges between those nodes. And so the efficiency of the job can easily be bottlenecked if the network performance is not meeting the needs of the internal computing. So how do you provision such capacity? Well, you have AWS, but then how do you maintain that capacity? And can traditional autoscalers really hold on to that capacity in a way that's going to work well for GPU workloads and ML workloads? And we'll talk about that very, very soon. So one by one, in terms of ML practitioners and the abstraction, we already discussed this. We have QFlow on AWS. The setup script will just completely abstract the whole thing. You will basically follow a simple list of commands, run it, and you will get a standard endpoint of QFlow ready to go. On the large data sets, that does require copying, but here's the good news. First off, we now have a driver for example, FSX Lustre. How many of you know what FSX Lustre is in a show of hands? So FSX Lustre is a distributed file system which is meant to be high performant but still shared across multiple nodes. So it's a read-many or read-write-many notion that a lot of nodes and a lot of processes, a lot of pods can actually access the same file system and typically provide millions of IOPS to the typical average workload. So with that file system, a lot of these workloads have started to leverage significantly FSX Lustre as their go-to platform to have that staged data. So the process only copies the data once to an FSX Lustre. And not only that, it can actually create that and provision that for you. And it can do so dynamically. And dynamically meaning that by using the API, it will actually generate a persistent volume and a persistent volume claim that you can then use within your Kubernetes code to access that file system. Or you can create it statically by just creating the file system first and then handing over the file system ID to the underlying code to be able to leverage. But in either way, an NFS Lustre has a very interesting property that it can actually shadow an S3 bucket. So you don't actually need to copy any of the data yourself. What you need to do is you need to have the customer or yourself as a practitioner put all the staging data in S3, which it already is, and then use that as a path for the new NFS Lustre file system to kind of cache all the data from that location. So all the staging of the data is actually done behind the scenes by NFS Lustre itself. And by giving you the integrated CSI driver, that will also get provisioned seamlessly for you through Kubernetes. As far as the distributed training, there is a framework called Horvad. That framework was originated by Uber and was open sourced. We're finding that framework to be extremely popular across our customers that are leveraging machine learning at that scale. And that's actually accessible to you today through QFlow itself. So it does nothing more than actually simplify the process of distributing the job in the TensorFlow across multiple GPUs or across multiple nodes or both. And finally, from a capacity provisioning, we introduced updates to a project called Escalator, which is a project that's providing you with autoscaling capabilities that are more tuned to machine learning and batch workloads than the traditional Kubernetes autoscaler or node autoscaler that you all know and well. So at that point, I want to introduce you to Mike Root, who I introduced in the beginning. So he's going to walk you over Escalator and some of the improvements we made there and show you a demo of how that actually works today with the cluster.
Okay. All right. Hi. I would like to walk you through a demo of Escalator. So Escalator is a cluster autoscaler that was built by Atlassian. It's an alternative to the Kubernetes cluster autoscaler, and we're really excited about it because it has the potential to really help with machine learning workloads. It was designed to be a batch autoscaler and to try not to move pods around. It's designed to grow your cluster as quickly as possible and try to keep it stable while your workload runs to completion. The two features I'd like to demo for you today, one is already released in upstream and one is coming soon. The first is integration with AWS Fleet. AWS Fleet is an API that can be used to acquire capacity very quickly and is particularly useful when you're using very popular instance classes, particularly like P3 classes, which are the big GPU instances that a lot of people use for training. Before we get started, let me just show you a little bit about what we're going to be working with here. It's going to be a lot of black text on this, or a lot of white text on the screen, and some AWS console. I've got a basic EKS cluster, and I've got 3 node groups in this cluster. One node group is completely uninteresting. That's our T3 large. That's just going to be running Escalator for us. I have a C5 X large node group, which is going to be used to run a CPU intensive job, and I have a P3 8X large node group that is going to be used to run a GPU intensive job. I started each node group out with a single instance. This is not because Escalator can't start from 0. It's more that when Escalator starts a node group from 0, it first must launch one instance, wait for it to warm up, and then scale the cluster out. So it's just going to be really boring if I make you wait through all of that. So let's take a look at our demo. So we have just a basic basic EKS cluster. AWS Node is our CNI, but the other interesting part here is the NVIDIA device plugin daemon set. What this daemon set does is it can run on any instance type, but if you have GPU accelerated instances, it will tag your instances with GPU capacity so that you can schedule your GPUs as resources just like CPU. So I'm going to run that everywhere on my cluster. Let's take a quick look at what a Escalator config looks like. So I've got 2 autoscaling groups, and these model the autoscaling groups I have in the console. One has a upper limit of 15 nodes, that's our C5 group. One has an upper limit of 2 nodes, that's our P3 group. I'm not going to go super crazy on acquiring a ton of P3 capacity just because these are really popular instances, and I don't want to limit that for anybody. So let's deploy this then. We're going to take a look at this. This is just the full version, so I'm not going to step through that. So let's deploy Escalator. And we'll see that Escalator has launched on our T3 instance. And let's just take a look at the logs we've got here. Yeah. There we go. So Escalator has, because we've configured it for our node groups, you can see that it knows all about them. It knows our upper and lower bounds. And because the cluster is in steady state, there's nothing to be scheduled. So no demands on CPU or memory. And this is going to poll your auto-scaling groups about, I've got it configured for once every 30 seconds, but by default, you can change. By default, it's 60 seconds, and you can change that. So let's deploy a workload on here. I've got a job that's mostly designed to just kind of sit and pin down some cores, just to give our cluster time to scale. The important thing to note about this is it requires 1 CPU and a gig of RAM. That's probably a little excessive, but it just gives us something to show on our cluster here. So I'm going to apply this. And that job will create a bunch of pods. And those pods are going to sit in pending state. And if we look back at Escalator, you can see that it has detected that there is a lot of work coming into the cluster and that it should be scaling up the cluster. So if we take a look at our AWS console, you'll see that it has acquired and already has running 15 new nodes. It's done this using the Fleet API. The nice thing about the Fleet API is when you request a set of nodes from it, the way Escalator uses this API, they will either all be immediately fulfilled to you, or you will be denied those nodes. So there's no more dial up the auto-scaling group, let capacity trickle in. You're definitely going to get it if that API call succeeds. And if it doesn't, Escalator will continue to retry behind the scenes at its normal polling interval. So those are all coming online in my cluster. We should be able to see those nodes. And yeah, so those are kind of trickle, or those are gonna kind of come online and join the cluster. They're just booting up and doing the normal bootstrapping work, letting the CNI come online. So we'll let that finish. Those are going to retire our work pretty quickly. Let's take a look then, while that's going, at a GPU job. So this is the same job we've got. All it does is pin down a core, but it also now has limits around GPUs. Each one of these jobs is going to try to hold down a single GPU. So I've started my cluster out with a P3 8x large, which has 4 GPU cores, and I'm going to try to run 2 of these at first. And so those pods are going to get running, and you can see them. You'll see them get scheduled on the existing GPU. And then if we take a look at our other pods, though, we should see that our Pi job got done, and Escalator will begin to scale down the autoscaling group past that. The first thing it's going to do is it's going to taint the nodes to allow the workloads to finish and drain off the nodes, and then it will batch terminate them. I'm not going to make you sit up here and wait for it, but you'll basically see, if we were to wait for it, you'd see all of those 15 running nodes, now that they have no pending pods, all the pods that were scheduled onto them are completed, will just be terminated, and your autoscaling group will go back to the minimum capacity bounds. There we go. And that's, those are the two changes. So we've got GPU-based cluster autoscaling, which will be committed to the upstream project hopefully pretty soon, within the next week. And we've got the fleet instant capacity acquisition, which is already in the project and should be released very soon. And then turn it back to you, Yaniv.
So let's talk about inference. So we talked about the fact that we require large-scale jobs. So on the training side, that boils down to distributed training jobs, multi-GPU, multi-node. What does that boil down into when it comes to workloads or inference workloads? So in autonomous vehicles specifically, there is no real inference taking place in the cloud. The inference will eventually take place in the car. But in order to build or simulate an environment which is as close as possible to the landscape that the sensors in the car are seeing, there needs to be a lot of simulations going on continuously, testing out the models in like simulated conditions under what we call like an artificially generated vision environment, which is as close as what we will get to what the car will actually see on the road. So those are what we call the large-scale simulation workloads. And I want to give you a little bit of sense of like what that scale looks like. And those are all CPU-based workloads. Those are not requiring GPUs, but they are running at a very large scale. So I want to talk to you about koalas. We always use that example because koala was a species that started to decline back in the 70s. So it's declined about 17%. And the university in Australia was very worried about how we can actually impact that survival rate. And what they've done is they actually conducted a research that examines few factors of how the habitat barriers and the climate conditions can actually affect what we call the DNA mutation or the evolution and the genetic diversity of that species. So in order to run that experiment, and that was just a few years ago, they had to sequence, I think, about 3 billion base pairs of their genome, and that required a lot of compute. So they used AWS and ran the whole thing on spot instances. And so that thing was running on about 3 million cores overall, averaging in about 500 to 1,000 cores in parallel in each step of the genome sequencing. So that was a pretty amazing and ambitious project at the time. And now I want to show you what the typical AV simulation workloads would require in terms of compute compared to koala genomics. So for those of you with a 20/20 vision, there is a short yellow line somewhere on the lower bar next to the word koala genomics, which you can barely see, because that is the scale that our customers are now starting to run in autonomous vehicles. And that is the amount of compute and the concurrent CPUs that they would require. And similarly, on the total requirement for the job, that's also running at a pretty different scale than what we've seen with that previous example that I showed. Now, I'm talking about autonomous vehicles, but this is starting to emerge in many, many other industries. So if you look at pharma, pharmaceutical companies, robotics, financial institutions. So a lot of those industries, and of course manufacturing and robotics, a lot of those industries are now starting to leverage machine learning at scales in order to solve a lot of those industry-specific problems that they have. So autonomous vehicles is actually one of the early ones that have reached those kind of scales, but this is definitely not the last ones. We are working with a lot of those industries to get them ramped up onto pretty much a lot of similar and common challenges, and actually involving a lot of the common models that these deep learning, it's important to say, it's not just traditional machine learning. Those are deep learning algorithms, which usually involve what we call convolutional network, CNNs or DNNs. And that's the reason why they are more complicated, require more computing power, and require those scales that we have just seen. So just to give you a sense, if I'm looking at here, these are the top 10 supercomputers on the planet as of today, and we're trying to measure that with what we call the amount of petaflops, the floating point operations that they can process. So on the bottom of that, we're at about 20 or 27 petaflops. So just to give you a sense, a single P3DN instance today at AWS can produce 1 petaflop. So if you take a network or a fleet of 20 P3DN instances, you have actually done or achieved what we call supercomputer scale in terms of processing. And this is basically where we want to be. We want to be able to provide our AV customers, and not just AV. You can replace AV with any other industry. A supercomputer scale, like one of the top 10 supercomputers that are available today for those kind of projects. So going back to the specifics, there are a lot of challenges involved today with setting up containers for ML. So how does containers fit into all that story? So think about this. If you're a practitioner and you need to run TensorFlow on one of our instances, how would you go about do that? Are you going to install your own Python? Are you going to customize your TensorFlow version? So typically, up until recently, we would provide what we call a deep learning AMI, which is our machine images. You would customize that AMI, install whatever frameworks you want on top of it. That could be a little bit tricky and therefore a little bit complex to some of the data scientists that have kind of told us that they don't want to be in the business of customizing Amazon AMIs. It's not their forte. So what we have done is we actually launched what we call deep learning containers in March. So deep learning containers are nothing more than a predefined set of containers that are coming pre-bundled with the frameworks that you require in order to run your machine learning workloads. So basically think a bit of it as a permutation of running your favorite framework like MXNet and TensorFlow, along with some characteristics that are more tuned to training or for inference, depending on what you want to run, more tuned to GPU versus CPU, and also with your favorite Python version, whether that's 2.7 or 3.6. So those permutations are distributed as specific containers that you can just take and inherit your base container from, and then add your custom code in order to run that. So that's available to you today through the marketplace and ECR, our container registry. So pretty much that's it for me. 2 callouts. One is if you want to get started with machine learning on AWS, this is kind of your, I would say, the simple getting started experience. We also have blogs that are more complicated for the more advanced users, but I would go, if I would get it started with this experience, I would get to that link first, check out the documentation, try out all the startup scripts, and make myself comfortable with the environment. Secondly, I am very well interested if any of you is running machine learning workloads today, whether it's similar to the way I just described on Kubernetes, or you're using some other framework, whether it's Amazon or another vendor, any way you want. I'm very, very interested to talk to you and learn from you on how you run today and what are the challenges that we can help solve for you in the future. So I'll be around here until the end of the day. If you guys want, you can come find me. Thank you so much.